Section 3.1. Today we're going to take a look at extrema on an interval. So the first thing that we need to define is what we mean by the word extrema. So we're going to take a function f, and it's defined on an interval I containing c. So I is some sort of length of space, right? You know, it's like -2 to 2 or something like that. And c is a point between those two endpoints. F of c is called the minimum of f on I, when f of c is less than or equal to f of x for all x and I. And f of c is the maximum of f on I, when f of c is greater than or equal to f of x for all x and I. The maximum and minimum values on an interval are the extreme values, or extrema. So extrema means maximum or minimum, both, of the function on the interval. Sometimes we also call them, in fact, we usually hear them called the absolute maximum and absolute minimum. That's what your book uses, but some textbooks will call them global maximum and global minimum. Okay? So we're looking for the words absolute with the textbook that we're using, and I want to draw you a picture, and it's exactly the picture that you think I'm going to draw if you were talking about maximum and minimum. You've got some kind of a curve, and my interval that I'm looking at is between here and here. Okay, so we'll say A to B. And the maximum is simply the largest y value on the entire curve. So it looks like on this one at this point on the left at f of A, right? That's our maximum on this curve. And the minimum is at this low valley point right here, somewhere sort of between 0 and B on the right-hand side in quadrant 4. Okay? Now, when we say maximum or minimum, we actually are referring to the y value. So it's actually the maximum is actually f of A in this case. And if we call this point, we'll give it a name C just so I can reference it, then the minimum is f of C. Okay, so you don't actually say the x value, you actually reference the y value when you talk about the maximum or minimum value. Now, you'll notice that those are two very different kinds of points. One of the points is simply the end point, right, the left-hand side. And the other one is sort of this interesting place where there's this dip, okay? Those are exactly the two kinds of places where our maximum and minimum can occur. All right, so extreme value theorem says if f is continuous on a closed interval AB, then it will have a maximum and a minimum. So continuous means it doesn't have what? What things can you not have for it to be continuous? Poles, asymptotes, which are generally speaking discontinuities. What else did you say? You can actually have sharp turns. That one's actually okay. We can't have derivatives on sharp turns, but you can have maxes or minimums. So that's a good clarification. Jumps. That's the last one. You got it. Okay, so no holes, asymptotes, or jumps for it to be continuous. Okay, sharp turns are cool though. Relative or local extrema. If there is an open interval containing C on which f of C is a maximum or a minimum, you can say that f of C has a relative maximum or minimum at C f of C. Okay, so the difference between absolute and relative is that when you're talking about relative, you're looking at a close area around a particular point. I don't know why I said particular twice, but you know, that's the way it goes. So if you're looking at a small interval, then you're relatively a maximum or relatively a minimum point. But when you're talking about an absolute maximum or absolute minimum, you're talking about a much larger viewing window. Honestly, a lot of times we're talking about the whole graph itself. Not always, but we could be talking about the whole graph itself when we're talking about absolute extrema as well.
So it's basically just the window that you're looking at?
It is. It's the interval on which you're looking, exactly. So when we're looking at relative extrema, I'll draw you a picture of this one as well. We can look at the whole graph for one. There's no reason to look at a specific interval. But let's say, for instance, this is our graph. Then these points are relative extrema. Because if you looked at an interval nearby on each one of them, they are the biggest or the smallest value in a nearby area. So I had this point in my life when we moved to Ohio. My parents came to visit. This was maybe about 10 years ago. And my mom believes that I'm tall. Okay? So for those of you who haven't stood up next to me, I am 5'4", and I'm probably shrinking at this point in my life. So I might not even be quite 5'4" anymore. And once I got there, my husband was youth pastor at the church we were at, and I promised every single youth that was in high school or above was taller than I was. And I just, was ready for my mom to get here so that she could see that I wasn't tall. But the reason that she thinks that I'm tall is because I am the tallest woman in my family. Okay? My mom's 5'2", my sister's 5'2", my grandmother was 5 foot. I have a sister-in-law who's 5 foot. Okay? So relatively speaking, she believes I'm tall. And in her world, with the people that she's with in our family, this makes sense, right? But we put me into another situation and I wasn't. It's a relative value. Okay? So that's what we have to look at. Come on in, ladies, when we're talking about relative extrema. All right, critical numbers then are places on our graph or in our function where the derivative, hang on a second. This has got a typo in it on my slide and on your, no, it's not on yours, but it's on my slide, f prime of c. Okay. So critical numbers are places where the derivative, f prime of c, is equal to 0, or the derivative is not differentiable. It isn't defined. Okay, there isn't a derivative there. The function's not differentiable. Then we call those critical numbers. So critical numbers, very specifically, are these places where we would have derivatives or slopes of 0. We change directions is what it ends up meaning. Okay, so do you see how the graph on those two circled in areas where I've got my red dots changed directions? They were decreasing and now they're increasing. If we were to draw a tangent line at those points, they would be horizontal, slope 0. So when we have those places where the slope is 0, we get critical points. We may have maxes, we may have mins, we may not, but we at least have what we call a critical point. That we can say for sure. So there are a couple places you might be like, well, how could we not have a max or a min? Well, one classic example is this graph right here. Do you remember what this graph is without me even putting it on a xy axis? X cubed. Y equal x cubed. If you took the derivative of this, it would be y equal 3x squared. And where is that graph, why is that equation, y equals 3x squared equal to 0?
Where is 0?
At 0, right? And if you sort of graphed this appropriately and very specifically, you would see that you actually have, this is not a good graph because I'm not a good artist, and I'm not even going to be able to draw my tangent line, but it looks something like this. There is a horizontal tangent line through the center of this graph, and it doesn't actually change directions. So we don't always get a max or a min, but we could. It's sort of one of those, okay, maybe now I have an option of where I have a max or a min. The other thing that it talks about in this definition is it talks about being not differentiable. And that's going to be what, Christian, you mentioned when you were talking about sharp turns. So this idea of a sharp turn. If you had a graph that had a cusp, that's what this is called, would that particular point stand a chance at being a max or a min? Yes. Yes. Is this graph, if this started and ended right here and here, what is my maximum point on this graph?
That little sharp line.
Yeah, it's the cusp here at the top, right? That point right there would be my maximum value on this particular graph. I know I don't have any axes here, but just imagine with me. This is the tallest point. It's the highest y value. So this actually also stands a chance at being a maximum or a minimum value. So we call it a critical number. Dawson.
Would the minimum be the bottom point?
On this one that I drew, it would be on the bottom left.
Okay.
Yeah.
That counts even if it's not like it.
Well, that doesn't count as a critical number, but it could still be a minimum. So what we're looking at when we're looking at critical numbers is we're usually looking at graphs that continue forever. So if you want to imagine that this graph went down forever from each direction, that blue point in the middle still could be a maximum, right?
Okay.
And then this graph might not even have a minimum.
Okay.
So we're only guaranteed maximum and minimum values if we have a closed interval. Take a look back over here,
Yes.
right? I meant to be highlighting there.
And if it's a critical number, then we aren't
If it's-
guaranteed.
If it's a critical number, it just means that it has a derivative of 0
Okay.
or the derivative doesn't exist. And those locations stand a chance at being maximum and minimum values. They're testing points is what they are. If you have relative extrema in a graph, they do in fact only occur at the critical points, critical numbers. So if we've got relative extrema, if there are somewhere relative extreme values on our graph, they will be definitely happening at these derivative of 0 or where the derivative doesn't exist locations, these critical points. All right, so these critical points are obviously important they're going to be giving us a lot of information about our graph. So the first thing we're going to do is to talk about how we find extrema in general, and that will include finding these critical points. So to find the extrema on a continuous function on a closed interval, okay? This is a closed interval. We will talk about open intervals. I think it's in 3.2. So on a closed interval, the first thing we do is we find the critical numbers of f and ab. So what does that mean? Well, we find the derivative and we set it equal to 0. Or we find the derivative and we find out where it doesn't exist. Maybe there's an asymptote, or maybe there's a denominator, maybe there's a radical that's got something funky going on. We look for places it doesn't exist. Now, practically speaking, 95% of the time, we're finding where the derivative is 0. The doesn't exist thing happens few and far between, okay? Not real often. After we find those critical numbers, those locations where the derivative equals 0, those x values, we evaluate them, okay? We find out what is their y value. Okay, I've got these sort of testing points, these runners up in the competition of maximum and minimum value on my graph. What are their x and y, or what is their y value? I've got their x values, what is their y value? And then the third thing I do is I check out the endpoints, because the graphs that I've drawn you, some of them had, this one over here, had endpoints that actually stood a chance at being the maximum and minimum values as well, right? So we also have to check out the endpoints. And then the least of those 3 or 4 or 5, however many you have, numbers is your minimum. And the biggest one is your maximum. Okay? So you're really testing 2 different kinds of points. You're testing critical numbers and you're testing endpoints. And if you forget to test one or the other, you really have chosen that you might be getting the answer wrong because you haven't really tested all the options. Okay? So let's take a look at how this works. So what we're supposed to do is we're supposed to find the critical numbers on this one. So we're not finding the maximum, minimum, we're just finding the critical numbers. So critical numbers are when what happens? When it changes direction potentially anyway, and when it happens when the derivative is equal to 0 or doesn't exist. Now this is a polynomial. It's not going to be having any problems because it's a nice continuous function, right?
Yes.
We like polynomials, they're great. So we don't have to worry about the doesn't exist on this one. We're just going to find the derivative and find out where it's 0. So what's the derivative of x cubed minus 3x squared?
3x squared minus 6x.
Excellent. And then what am I supposed to do with the derivative?
Equal to 0.
Set it equal to 0. Now, this is the point when some of the things that you have been doing on cleaning up derivatives is useful. Of course, there's nothing specifically hard or difficult about this one, right? But sometimes there have been places where I've said on the derivative gateway, you don't need to simplify, I'm just curious, do you know, not curious, but I want to make sure you know how to do the derivative. And then we've been homeworks, tests, and quizzes and so forth, we've been working on the cleaning up, right? And I've said there's going to be a reason for the working on the cleaning up, and this is it. Because it's going to be a lot easier to solve something set equal to 0 if it's cleaned up. Okay? So in particular on this one, if we're trying to find out where this is equal to 0, thinking in terms of algebra, what do you have to do to find out where this is 0? We don't want to move over the 6x actually. Factoring. Okay, so if it's linear, we would move it over and we'd solve and we'd get one answer. And sometimes that will happen. But if you've still got a polynomial, if you've still got anything that's got more than just plain old simple x to the first power in it, then you want to work on factoring. Okay? This one does have things in common that can be factored out. So what can I factor out of 3x squared and 6x? 3x. And if I factor 3x out of 3x squared, what do I get? X. And then minus 2. Okay, good. And then what we're going to do is set each piece equal to 0, right? This feels like algebra, doesn't it? You betcha. So what are my 2 x values that are my critical numbers? 0 and 2. So if I were moving on with this problem to find relative extrema, these are the 2 possible, they're the first 2 contenders at being relative extreme points. They are the critical numbers, exactly. These are critical numbers.
Was the maximum minimum?
If we were looking for that, yeah, then we would continue. The next problem we're going to continue. Yeah. Okay, so critical numbers. When you're going to have some questions that they're going to ask you in your homework that are going to just say find the critical numbers. So don't gloss over the directions and end up having to do like 10 times more work than you had to. Okay, make sure that you're being aware. If it said critical numbers, I'm done with this problem. Right? Okay. Next one doesn't say that. It says find the absolute extrema. So that's going to involve several more steps. However, it starts at the same place that the last problem did. I still have to find critical numbers. So this one, again, is a very nice function. It's a polynomial. What is the derivative of this function? Awesome. And what am I going to do with this function? Set it equal to 0 first. Yep. Now this one, Dawson, is line, right?
Yes.
So we can just, there's no factoring I have to worry about with this, right? Because I don't have a polynomial. I mean, it is technically a polynomial, but it's a line. Yeah, so we can just move it over. So I have negative 2x equals negative 3. X is 3/2. So this is my critical number, yeah? All right, so the next thing that the sort of list of steps, if you will, that I had before that I need then is what? Find the y value that goes with this. In other words, what is f of 3/2? So grab your calculator out. We're going to let our calculator help us out for these. There's absolutely no reason not to, because we're going to be evaluating 3 points in our function. Now, I only wrote down one of them. Why am I saying I'm going to evaluate 3? We need the endpoints too. So take your graph, or take your calculator, and in y, my suggestion would be to just do this in y1, to type in negative x squared plus 3x and minus 5. And then you can go into your table, and you can put in 3/2, or 1.5 if you like that number better. Yep, put the equation in y1. That's what I did. And then I used my table to plug in 3/2. And it's a nice decimal value, so I'll go ahead and use the decimal value. I'm getting this.
Do you want the fraction? That's what I got.
Either way is fine. It doesn't really matter. If the fraction, if the decimal is not a terminating decimal, then I definitely would want the fraction. Like, I don't really want you to write down 11.333333 or even a 3 repeating. We don't do that in mathematics. You know, like my elementary ed people, we talk about it in that fashion, but in mathematics at this level, I almost said real mathematics, it's not really what I mean, but at mathematics at this level, we don't do that. We don't do repeatings. So we would put a fraction in that form. So this one is the decimal expansion for it. What did you get for the fraction for that one, Garrett?
Negative 11/4.
Good. Okay, so either version of this is fine. In some sense, the negative 2.75 is a little bit more helpful because we're going to be making some comparisons, and it's easier to compare numbers in a whole number or decimal form than it is in a fractional form. All right, what are the other numbers I'm supposed to be testing? The endpoints, which are negative 2 and 1. So we're going to test those points as well. Okay, I think those are my values. Are those yours? Fantastic. Okay, which one's the biggest value? That's actually the smallest.
Oh, yeah.
Because,
Negative 2.75.
yeah, this one's the minimum, right?
Negative.
And the maximum is the negative 2.75. So this is my max. All right, so you might be asking yourself then, well, how do I write the answer down? Well, remember we talked about it's the actual y value that's the max or the minimum value, not the x. So you can say a couple of things, and it depends on the blanks they have you fill in and so forth. But the max is actually negative 2.75 or 11/4. And oftentimes they'll have you tell it at what x value that happens, and this happens at x equals 3/2 or 1.5. I'll go with a decimal since I used a decimal on the other one. And then the minimum is negative 15. And this occurs at x equals negative 2. So this is really like your answer to the question. The maximum and minimum values, if that's all they ask for, though, are the y values.
What is the negative 3? What is
The negative 3 is just going to be one of the endpoints. It'll look much like when I had this one over here. Whoops, one more, I think, back. Do you see how this endpoint's not a maximum or a minimum? It's just an endpoint. That's okay. That's sort of what our graph is going to have. It's not going to look like this, obviously, but it's going to have a location where it's not a max or a min at that particular endpoint. Okay. Let's try another one. Same directions, absolute extrema of the function on the closed interval. So what's our first step? The derivative. We're going to do the quotient rule. That would work. Okay, so what is going to be h prime of t? Walk me through it.
T minus 2 times 1.
Why is there a little
And
line
there's
after the two? That's
It's a comma.
Oh, it's a comma.
It's a comma. It's separating the function
Oh,
from the
okay.
interval.
And there's 1.
Yeah, it does kind of look like a prime.
know.
Sorry about that. Okay, Dawson, what do you want to continue?
1 times t. All of this. Oh, and then times. No, that was it.
I think you're okay.
Over T minus 2 squared.
Awesome. Okay, does anybody have any questions about the pieces, where they came from, or anything like that? So what I've graded so far of your tests, the derivative rule for quotient rule looked pretty good. So I think you guys are pretty good on that one. All right, cleaning up the numerator. This is t minus 2 minus t over t minus 2 squared. Please do not cancel out the t minus 2 in the numerator and the t minus 2 in the denominator. You can't do that. Because in the numerator, you've got addition and subtraction that are joining them, and not multiplication, okay? So we do need to simplify the numerator as it is, which will give me what?
-2.
-2 over
T minus 2 squared.
t minus 2 squared. Okay, so now what happens if I try to set this equal to 0?
You get the whole asymptote. T cannot be equal to 2.
Okay, so you guys are answering lots of good things, but not exactly what I'm looking for, because it's not exactly the question I asked. Where does this function equal 0? Nowhere. Did you see that, Garrett?
Yeah.
Yeah, the answer is actually nowhere. We can get the denominator to be 0, right? And we will look for that in a minute. But it's the numerator being equal 0 that makes the whole fraction equal to 0. And this numerator cannot ever equal 0 because it's a constant. So this is not going to happen that it equals 0. We are supposed to test the other option, in particular, about finding out where things don't exist, right? Where does this not exist?
2.
Yeah, t equals 2 if we use the variable that we started with. But yeah, at t equals 2, it doesn't exist, right? But what's happening at t equal 2? Original function, look at the original function. What's happening? There is an asymptote there. How do you know?
Because if you put 2 in, there's undefined.
Yeah, because there's no way to simplify the numerator and the denominator to cancel it out. We did that in the first exam, right? You guys looked at removable and non-removable discontinuities. This is a non-removable discontinuity. So this is definitely an asymptote. So if it's an asymptote, hang on, let me write that down before I keep talking. If there's an asymptote, it's not going to be a location where I have a critical point. I don't have a maximum in there. I have an asymptote there, right? So it's really not going to give me a critical value because the value that it gives me is not actually even in the domain of my function. Are you guys with me?
Yes.
Okay, cool.
So does that
All right.
mean your endpoints are automatic?
Yes, it means my endpoints are going to have to be the answers to this question. One of them is going to be the max and the other one's going to be the min. Exactly. So let's take a look then. We're going to use those endpoints. What were they? 3 and 5. H of 3 and H of 5. If you want to plug them in by hand, you can. I think this one's pretty easy to plug in by hand. You can use your calculator if you really want to. But if I use 3 in the numerator and 3 in the denominator, 3 over 3 minus 2 would give me 3. And then 5 over 5 minus 2 gives me 5 thirds. So what's my max? Which one?
3.
3 is the max. And that makes 5 thirds my minimum value. So again, if I were writing this out, sort of properly, if you will, answering the question as it was asked, my maximum is what?
3 at
My maximum is 3
H equals 3.
at t, actually, right? At t equal 3. Was it 3 and 3? Yeah, it was.
Do you usually write it as a point?
I don't have a problem with that. So I say that, but let me be careful about that. Let me finish writing this one, and then I'll show you the sort of the pros and cons of what you're asking. The minimum is 5 thirds at t equals 5. Thank you.
Is it still absolute? Like
Yes, these are absolute values because we're on an interval with endpoints that we're testing. So they're not the absolute values for like the whole graph if you were sort of going outside of the 3 to 5 interval range, if you will. But they are for this window that we're looking in. Fallon, to answer your question, can you write it as an ordered pair? It isn't exactly wrong, except that I don't want you to have some sort of misconception that the maximum is the point. The maximum is the y value at the point. Do you see the difference? So if you wrote it that way, I probably would take off something because then I wouldn't know whether or not you actually recognize that the maximum value is, say, for instance, 3 here and not, or 5 have, the minimum value is 5/3 as opposed to it being 5. That's sort of the problem. So, okay, we have one more, and as is always the case, we got to get some trig in there, right?
Sure.
Man, you guys are just killing me about your trig. Trig is so much fun. Boo. Oh. All right, we have a closed interval. Think for a moment with me about trig functions. This one's cosine, so we'll just talk about cosine. What about maximum and minimum happen on cosine that you're aware of? What is it?
Happens over and over.
Over and over and over again, right? These curves, and it's true for any trig function. Whatever you have, it's a repeating function, right? They're called periodic. That's the word you used for them.
Tangent.
Even with tangent, if tangent were used, you would actually have to be completely contained between one set of asymptotes, right? And you'd have to have the endpoints be actually, between those two values. Otherwise, it'd be negative infinity.
I don't know if I see it.
With tangent, it would look something like this.
Like x cubed.
Yeah.
It's executed.
Yeah, that's what.
And the problem, so to speak, with doing that is that your asymptotes, that's too light to see. Let's try that again. Your asymptotes here, okay, imagine. I can't get too close or it's not letting me. Imagine, those are asymptotes straight up and down, but my capabilities of my iPad are being uncooperative. Okay, so these are straight up and down. So if you overlapped an asymptote, you wouldn't have a closed interval because the function would not be defined everywhere. So at the very best, you would have to have a function defined like in between here, right? And not including those endpoints. So it would have to be a closed interval. So it would actually be kind of like the function we just did where the maximum and minimum would have to be at the endpoints because we have no other choices for our tangent graph. It's true for cotangent as well, by the way. Yeah. This one's cosine, though. So let's take a look at cosine. We proceed with the same kind of process we did before. You will take a notice, though, that this is cosine, and it's going between 0 and 2 pi. And the period for sine and cosine is 2 pi. So we do expect a full rotation of the entire cosine curve between there. So we're going to do the same thing as before. We're finding out where does this derivative equal 0. So what's the derivative of 3 cosine of x?
Negative 3 sin x.
Excellent. Negative 3 sine of x. And we're going to set it equal to 0. Now, does the negative 3 matter?
No.
No. I could sort of divide it to the other side. The same question could be asked to say, where is sine of x equal to 0? You can play with your calculator to find that. I would hope that this one's a clean enough one that unit circle would pop in your mind to use that as a better choice. Where on the unit circle is the sine value equal to 0? Between 0 and 2 pi.
0.
At 0, at what's next? Pi, 2 pi. And because we're going between 0 and 2 pi, we're done. Now, technically, could we write down 3 pi and 4 pi and 5 pi and negative 2 pi and negative 3 pi? Absolutely. But we are working on an interval, correct? So we only care about the values on the interval. None of the rest of them really even matter. It's worth noting up here, did you notice that a t equal 2 value where my asymptote wasn't on my interval either? Yeah? That's actually really important because otherwise I wouldn't have the function defined everywhere in between. So that's a very valuable piece of information I failed to mention. Okay, so we have 3 values, and it happens to be that 2 of them are the endpoints that we were going to test anyway, right?
Yeah.
Yeah, so that's kind of interesting. Doesn't always happen that way. So we're going to test g of 0 and g of 2 pi because they're endpoints. And then we're going to also test g of pi because it's the point that's actually where the derivative is equal to 0 that wasn't an endpoint. And as you're doing this, be careful that you're testing this into g, not into g prime. So this is 3 cosine of 0 3 cosine of 2 pi, and 3 cosine of pi.
0 and 2 pi.
Yeah, 0 and 2 pi are the same thing, right? So what is the cosine of 0?
1.
It's 1. So then I've got 3 times 1. This value would be 3. Cosine of 2 pi, because of the periodic nature of the cosine graph, and if you think about it, if you're over here at 0 on your unit circle and you go all the way around to 2 pi, you're back at the same location, right? What's the cosine value there then?
3.
Still
Also,
3. Yeah. Well, it's actually 1, but then times our 3 that's there. Exactly, yeah, so 3. And then what is the cosine of pi?
Negative 3.
That's -1 times my 3, so I have my -3 exactly. So actually, the way that this is that I actually have 2 maximums, don't I? Should that surprise us?
No.
Probably not. It's a cosine curve, right? It's periodic. And then I've got 1 minimum. Yeah? Okay. So I'm going to be able to write down that I have an absolute max of 3 at x equals 0 and 2 pi. And I have a minimum of -3 at x equals pi.
Okay. Is this one of those things where we get to the homework and it's like, whoa?
The only things that will happen differently on the homework is the functions are going to change, right? The directions will still be of the same variety. It's either going to be finding the maximum minimum points or finding critical numbers themselves. And remember, please remember, look how much less work the finding critical numbers is.
Yes.
Okay? So be aware of the directions and make sure you're following the directions that you're given. So you're finding critical numbers and you're finding the maximum minimum points. And that's it. Okay?